Durham of Experiment and Theory.
Hi, yes. First I'd like to thank the organisers for inviting me and giving me the opportunity to speak today. It's really nice to be back at ITAMP. I was here for the laser cooling molecule, or the ultracold molecules meeting 3 years ago. I thought I would start this talk in a slightly different way by introducing me. Some of you hopefully know who I am, some of you might not. So I did my PhD on laser cooling calcium fluoride with Mike Tarbert and Ben Sauer at Imperial College. And I worked on molecules for about 5 years. In the interim, while everyone's been busy with COVID, I left. And I went and I worked at the Institut Optique in Paris, where I worked on the Rydberg quantum simulator. So I worked there for 2 years before coming back to the UK as assistant professor at Durham, where I thought I'd start a new laser cooling molecule experiment working with calcium fluoride. So I'm going to talk to you about what I've done in the last year. And mainly, we've been building a new lab. So there was no laser cooling molecules at Durham. There still isn't, but there will be. So January 2022, so I'd been around for a couple of months, and this was the state of my lab. It was a former reception room where all the deliveries came in. That's now stopped, luckily. And we've been, well, not we, professionals have been building my lab for me. And as of September, it looked like this. So quite a drastic upgrade. And we got the keys, as it were, the code to get into the lab in September. So the other thing that you need to build a laser cooling molecules experiment, other than a lab, is money. So I've spent a lot of this year applying for various grants. Luckily for you, I'm not going to talk to you about the British funding system or the process of writing grants. So I've been keeping myself busy with things that you can do towards laser cooling molecules with neither a lab nor money. So this is the outline for my talk. So I'm going to start off by talking to you about what progress we've actually been making towards building up the laser cooling molecules experiment. I'm then going to talk a bit about theory. I've never been in a theory section of a conference before. So maybe I should add the caveat, this is theory for experimentalists. And then I'm going to finish by going off piste. And although some people did break tradition yesterday and talk about bialkalis, so I have been involved in the RSCS tweezer experiment at Durham. I'm going to tell you a little bit about the recent results that we've had on that experiment. Okay, so what can you do towards your experiment? Well, we decided to start off by just thinking about the locking schemes. So everybody is now, after the last 2 days at least, painfully aware of how many lasers you need. Diatomics are bad enough, polyatomics, wow. Good luck to you guys. So we've been thinking about how we can make a locking system that's cheap and replicable. This is a scheme of this year of my life, is how can we do this as cheaply as possible. So we decided that we're going to go the usual route, and we're going to use a transfer cavity locking system. So for those of you who don't know, this works in the following way. So we have a reference laser. Luckily, there's lots of 780 lasers lying around Durham, so I could just take one from someone. And we can set up a saturated spectroscopy, and we can feed back and lock the reference laser to a transition in the rubidium. We then inject this laser beam into a scanning Fabry-Perot cavity, and we can detect the peaks coming out the other side. So here we've got these two large reference peaks. So those are the peaks of the 780 laser separated by the free spectral range of the cavity. We can then inject another laser Here, you'll notice another 780 laser that was lying around. We can inject that laser into the same cavity, and what we want to do is we want to stabilize the separation between this follower peak and the reference peaks. There's nothing new here, really. We decided that we would do all of the signal control and the calculations using an Arduino. So we feed in the photodiode signal, the Arduino identifies the peaks, identifies the arrival times, calculates the ratios that we want, and then outputs a voltage back to the laser to control the locking. We can lock both this separation here, so getting the follower laser locked, but also locking the cavity as we want to control against drifts that happen over the long time scales. And my PhD student worked on setting this all up, and you can see from this plot here that she's, the follower laser was nicely stabilized with this method. This we based entirely on this paper here, where they wrote some code to do all of this for us. Now, this works really nicely if you have one single follower laser, because these Arduino Duo boards have two digital to analog converters, so you can have two outputs, one to control and lock your cavity and one to lock your laser. For us, obviously, we don't want to then have a whole nother setup for laser 2, a whole nother setup for laser 3. That's kind of defeating the object of making this as cheap and replicable as possible. So the technique that we decided to go for was to use a sample and hold multiplexer chip. So this works really nicely. We need a single voltage input and an address decoder. So this is just 3 digital pins. And then depending on what the state of these pins are, we can send a voltage out through one of the 8 outputs that we have. So the idea is that we will use one of our DAC outputs on the Arduino to give a time varying voltage. And then we will change our address, and we will, at time 0, we will send voltage 0 to output 0. Then at time 1, we will send voltage 1 to output 1, etc., etc. And we can cycle through this very quickly, and we can lock all of our lasers using this single chip, which requires very little changing to the Arduino code, which my PhD student was happy about. So she's been testing this out recently, because what we were worried about is, what happens when we go from this state where we're sampling, where we've got this circuit connected, to the state where the chip is just holding. And this is a plot showing, so the red here is showing the digital pin A, where B and C are left at 0, and it's changing between controlling output 0 and controlling output 1. And then in orange we have output 0, and in green we have output 1. If you look at it on this scale, it looks kind of flat, it looks kind of nice. We can zoom in, and we see that we do get these little steps as we change between being in the hold configuration and being in the sampling configuration. These steps are on the order of about 4 millivolts, which is what is given by the spec sheets. And so we think this is probably not going to be a problem, because that's not going to correspond to very much in terms of frequency, but there's a few things that we can do later down the line when we actually have lasers to control and we can test this out properly. The other thing that we looked at was what is the droop. So if you sample for, here we're sampling for 10 milliseconds, and then we're just holding for 2 seconds, and we were wondering how much is this signal going to change over the timescales of 2 seconds. And it was slightly surprising. It really changes very, very little. So once you've set the voltage on one of these outputs, it's pretty good, even though you're no longer actively updating it. So this bodes very well for controlling the lasers, and we hope that at some point we'll have some lasers we can test this out on. Okay, so changing gears. The theory that we've been working on, well, earlier this year there was a nice Python module output by the Durham group where they were using it to calculate the ground state, so the 1 sigma state of molecules for bialkali experiments. And well, I thought, wouldn't this be nice if we had a similar module for laser coolable molecules? So I've been working on this recently. I'm sure that everyone has in their own lab their own versions of these, but we're getting more and more molecules, more and more experiments being set up all the time, so maybe this would be a nice tool. So what it can do is it will calculate the rotational hyperfine Zeeman, DC Stark, AC Stark shifts, and it's working in the coupled basis 100 case B. So far, I've managed to implement the hyperfine structure, the effect of static fields, the effect of optical fields, and I'm now working on transition dipole moments. This is a work in progress. If people have things that they think would be useful to add into it, I would be very open to having discussions about that kind of stuff. And just an example here is the DC Stark shift. Calculate your angular momentum transforms, write it up in Python, and you get your shifts that you want to see. Okay, so the last couple of minutes, I'm going to talk about the RSCS experiment. So this is laser cooling of atoms. And the starting point is we have individual species selective tweezers. So we can load tweezers of rubidium, and we have 2 tweezers of cesium, and we can detect them with high fidelity. We can control their position. And just to demonstrate this in the kind of, say, à la française, the way that we did in Paris is, you have your Eiffel Tower, which we built out of atoms. We also made the Mona Lisa out of atoms. So when I moved to Durham, I thought what we have to do is make the Angel of the North. So this is a 1/40,000th replica of Antony Gormley's statue. But we've also been doing more useful things. So we've been implementing Raman sideband cooling of the 2 species, and we've managed to create a robust enough sequence to cool both species at the same time and across multiple traps. So we can get 90% of our atoms into the motional ground state of their respective tweezers. The next thing that we have to do is we now need to overlap these tweezers. So we use an AOD to move the cesium tweezer, and we do this without, we try and heat the atoms as little as possible in this process. And then we load them into the same tweezer, transfer them into a 1064, and then we want to make a molecule. And the method that we use is Magneto Association. So here we have a applied external magnetic field. We then sweep this field across a Feshbach resonance, and we can form a molecule. And in the last couple of months, we've done exactly this. So here we have our molecule signal as we sweep across this Feshbach resonance. We go from the free atoms into the molecules. So this is very exciting for us. We now have molecules in the ground motional state of the tweezers, and the next stage is to apply stirrup and change these from a Feshbach molecule, which is very weakly bound, into a ground state molecule, and continue down that road. So to summarize, I've had a new lab built for me for laser cooling molecules. We've been working on an Arduino-based scanning transfer cavity lock, as well as a Python module for doublet sigma molecules. And I've also been working on Raman sideband cooling of dual species tweezer arrays of rubidium and cesium. And we've recently demonstrated Magneto Association of rubidium cesium molecules in tweezers. So with that, I would like to thank my PhD student who's been working away in the back corner of an old lab for the year, Bethan, and then the rubidium cesium tweezers team led by Simon Cornish, and theory help when I get stuck with doing matrix transforms Jeremy Hudson. So, and thank you for listening.
Thanks, Hannah. I'm sure there's some questions.
Did you say which molecule you want to laser cool in the long term?
I did not know. I'm going to go for a calcium fluoride molecule. I decided not to tempt the fates by saying too much about what I want to do until I've got some funding for it.
Yes, what might be limiting the efficiency of molecule creation for lithium?
So the main limiting factors are the ground state cooling. So here, I didn't explain this, but this is if the motional level is we say 2, but if it's not 0, then we don't make a molecule. We really need them to both the atoms to be in the ground motional state of the trap. So the Raman sideband cooling is not 100% efficient, and then also the preparation of the MF states of the two atoms beforehand is not perfect, and so that's what's limiting us here. Well, this is not my experiment. This is Simon Cornish's experiment. I am a laser cooler from my history, and you can't go to Durham University and say you're going to start doing association, because they'll look at you and go, oh well, Simon's already doing that. It's the diplomatic answer.
I'm curious what the bandwidth on the Arduino is. How often can you update?
So the Arduino is, I think it works at 17 megahertz. So the Arduino is not the limiting factor here. The sample and hold needs 3 microseconds to set its voltage before you can put it into the hold. So that's the slowest part.
So, and just to speculate, what do you think the individual update rate should be on a laser to keep it stabilized? Like 100 hertz, do you think would be okay?
Yeah, definitely.
So you could really think about multiplexing this to lots and lots and lots of channels.
Yeah. I think the cavity can only run at like 50 hertz. So at some point that is going to be your limiting factor.